So up here at the top, we have a prototype for this function called testfunc. This is that function we were talking about that's going to be called from within the ASM block. We'll see that here in a bit. And then in main here, we started out by declaring the structure called package. And then the first block here is just kind of testing out several different things, including referring to things from this structure definition. But we started here, so we defined the structure, in this case within main, and then we defined several different variables here in an array. And then we hit the ASM block, right? And again, the syntax here, at least in this is for Visual Studio anyways, is 2 underscores and then ASM. And then we hit the left curly bracket. And there's just several things in here to kind of test out the basic idea. But similar to the things that we started talking about in the Word document, really we're just referring to the different variables up here from the C++ level. We're referring to them directly by name inside this ASM block. So at the beginning here, we pushed, ESI and EDI, and then you'll notice that we're doing a bunch of move instructions next, such as move this value from the structure object into EAX. And then here we're testing out things like the length operator, which we can use instead of length of if we want to get the length of something. Here we're testing out the type operator, which can be used. And then here we have the size operator, which we said was an alternative to size of. And then here we're using that, that LEA, or load effective address, right? That was your alternative to the offset operator. And then going back to what we said in the Word document, that if you're going to be working with those ESI, EDI, EBP, or perhaps ESP, that those registers certainly do need to be, by the time the ASM block ends at least, need to have their original values preserved. So here, that's also why we did some pushing and popping of your ESI and EDI. But EAX, for example, we did not bother with saving and restoring because that's not going to cause us any problems, right? So we can just freely change, right, EAX or, for example, EDX here without any concern there. And then here we just ended that first ASM block. So again, just kind of a lot of different move instructions and a few other things here in that first ASM block, just kind of testing out some of the different things. And then we came back because this ASM block was first defined here, and then it ended here. And then we defined, right, some new variables at the C++ level, and then we hit another ASM block, right? So it is possible, as we said, to certainly alternate or go back and forth, right, between C++ and the embedded assembly with the ASM directive. And then again here, I'm just testing out a few more things. So we're referring to some of the variables in this case. So here we moved the literal value 5, for example, in the EAX, moved Y's value in EBX, and then added, and then here we're referring to the X variable from the C++ level, right? So add X3 and then add Y4, for example. And then we came down here to this call to test function. But the whole idea is that we were thinking about the issue of parameter passing through the runtime stack. So the idea is that these arguments, right, X and Y, are what we're sending into test function. So the idea is that we want to print out both X and Y. And now the way this works here, when we're wanting to set up parameters through the runtime stack, is, for example, you'll notice here we're pushing two things back to back, right? One is the value of the Y variable, right, meaning the Y variable from the C++ level, and then one is the value of the X variable, meaning the X variable from the C++ level. But you'll notice that we're pushing them in this order, right? Y first, and then X second. And so the idea is that Y corresponds to B here, and X corresponds to A here. So that should always be the order that we push things to get ready for that function call, because that's how C++ handles the parameters, right? So the in this case, right, the one that was pushed the most recently is the first one here. So we pushed Y first and then X, and then we called test function. And then the function itself just does a quick cout statement where we print out the value of A right first and then B second, where A would correspond to the X and then B would correspond to the Y. But then you'll notice this instruction that comes right after the call instruction that says add ESP8. So that was the cleanup work that we were talking about. And you'll notice in this case, we are directly referring to ESP by name, but we're doing a very specific thing to clean up the stack, right? We're not, we're not just sort of arbitrarily moving a random value, right? We're doing a very, very specific thing here that's to clean up the stack. And the idea is that we have to think about these two push instructions. So we push these two values, hit the call instruction, right? Run through this. When we hit the right curly bracket, because whether you return a value or not, you still ultimately go through the general return process where you have to look at the return address to get back to where you left off, because that's how we're going to go from here and then go back to the add instruction right after the function call ends, right? Because when the function ends, meaning when we hit the right curly bracket, we're going to pop that value off the top of the stack and then place it into EIP, right? And then that's how we're going to get back. But that's not enough by itself, right, to clean up the whole stack, because what about the values of X and Y? We don't want to just leave them sitting on there when we're done using them. And so this is one way of cleaning that up, right? Actually, just one instruction here, which says add ESP8. And we can think about why that's going to be okay, right? We can think about why that's going to work out for us. Because in chapter 5, we did a lot of pushing and popping as pairs, right? And in this case, you'll notice that there is no pop, although that would be another way of potentially handling this, would be perhaps two back-to-back pop instructions, where you might, for example, pop into X or pop into Y. But the idea is that we don't really have to do it that way because of the way this worked out. We already have, of course, the values in X and Y. Those came from this 4 block of instructions. And then at this point, we were just pushing them on the stack. And so we're not really wanting to put them anywhere else. So there's not really a specific need as far as popping them into some other place, but we do nonetheless need to clean up the stack. So, but the stack really just comes down to ESP, right? And what it's pointing at, because whatever ESP is pointing at, that's what's considered the top of the stack. And we also know from our discussions back in chapter 5 that also the pop instruction does not actually remove anything physically from the area of memory where it was stored, right? All pop really does, for example, when you say pop EAX, is one thing that happens is that you add, right? You add ESP to move the pointer up, right? And at the same time, you're going to take the value that was previously at the top and you're going to move that into EAX. But the value is still going to be at that area in memory as well. And the only way that that's going to change is if we later do maybe a push operation and add a new value there. So when we talk about cleaning up the stack, right, what really matters is ESP, right? ESP is what everything revolves around with the stack. So as long as we update the address in ESP in the correct way, right, that's really all that matters here as far as cleaning up the stack. And so one way to do this is we know that we pushed for X and Y, we know that we ultimately pushed 2 D words back to back, right? Meaning two integers, which correspond to D word, right? Or 4 bytes or 32 bits. So we know that we did that. So we can actually just do this with one instruction, because if we add 8, right? If we add 8 to ESP, well, then the whole idea is that when this whole block of 4 instructions is finished, when we do the add 8 to ESP, now ESP is going to be at where it was at before this first push Y instruction happened, which is exactly what we want, right? Because when this whole block ends, when this whole ASM block ends, the important thing is that ESP is where it was at prior to changing it through things like the push or the call instruction. So that's the sequence that happens here. So we know that the return address, because by the time we hit this call instruction, we've really pushed 3 things back to back, right? We pushed Y first, then we pushed X, and then the call instruction itself, right, pushes the return address, meaning the address of this add instruction. So we push those 3 values back to back. The function itself is going to automatically remove the return address and then place it in EIP so we can get back. But then we still have the additional cleanup work of removing these 2 things from the stack. And again, you could do that potentially with 2 back-to-back, pop instructions, but you can also just do it with this add ESP8. Given that the most important thing here is simply that we change ESP. So we're assuming this in this case that we don't need to actually take those values from the stack and place them somewhere else. All we're saying here is that we need to update ESP in the correct way. So add ESP8 is another way to accomplish that. That's going to clean up the stack for us. So that's the additional work that's being done here. But this is just the most concise way in this case of cleaning that up, is just rather than doing 2 pops, just adding 8 directly to ESP. And then that's going to get that pointer back where we need it by the time by the time the ASM block ends. And that's really what we're doing here in the second block. So just kind of moving some values initially into EX and EBX. But then we're changing both X and right, we're adding to both X and Y, meaning the X and Y variables here. So we're adding 3 to X's value, which was 5, right? So then we're going to get and then we're going to get 8, and then we're adding 4 to Y's value. So then we're going to get then we're going to get 10. And so then the idea is when we call this function here, we just wanted to print out both things, right? So 8 and then 10 here for A and B. And then we come back and then there's yet another cout statement directly within the main procedure, again, of X and Y directly. And then at that point, we just end the program. So just also showing things like how you can think about a function call when you're doing things like calling a C++ function that takes in some arguments from within an ASM block. That's fine. We just have to think about the issue of passing parameters through the runtime stack, and at the end also cleaning it up. So, and again, this idea is also extendable, right, in terms of having maybe more than 2 parameters, because if you had like maybe a third parameter here, like a int c, for example, well, then you would have 3 things that you would push before the call instruction, and then you would add 12, for example, to ESP instead of 8 to do the cleanup. Right, and again, we're adding 8 just because we know that each of these arguments is 4, and since we have 2 of them, it's going to be 8. But if we were doing something like 3 integer values, we could push all 3 to the stack back to back, and then have add ESP12 as the cleanup instruction after the call. Okay, so again, just a short program, just a few lines really of actual output here when we run it. But the first block was just kind of testing out these different things. And then the second block was testing out things like a basic function call that's happening within the within the ASM block. Okay, and then our output here is first we get 8, 10, right? That part was coming from the function call to test func, where we had that whole cout AB, where A was going to correspond to X, variable X from main, and then B was going to correspond to variable Y from main. And then after that ASM block ended, we had a cout statement also with those 2 variables as well, directly within main. So that's where we get the X:8 and the Y:10. So really, between main and the other function, we're just printing out both values twice. And so that's the only output in this case of the program. But so that gives us a basic idea of, how to think about things like embedding assembly directly within the C++. And including things like how a function call might be handled when the assembly block needs to call at some point one of the C++ functions. But another thing that also comes up, and this will be similar to your assignment this week, another thing that comes up also, though, is the issue of separate files. Because maybe what we want to do is we actually have a defined procedure at the assembly level that we want to call. So here, because really which way you're going to do it kind of depends on what you're doing. Again, the ASM block is convenient maybe if we have, just kind of a short block doing certain things. But, if we have maybe some sort of major operation, and especially if we're going to do that operation maybe many times throughout the program, then what we might actually want to do is have that defined as an assembly procedure, and then be able to call that procedure from within the C++ program. So that's another possible way of combining the 2 as well. So instead of just always using the ASM directive and embedding the assembly code in the same file as the C++ code, because that's exactly what we did here, is we have just this one CPP file that has everything, right? Both the C++ code and the assembly code. But sometimes we might want to actually define the assembly code in its own procedure, right? That's going to also be in a separate file from the C++ code. But the C++ code will be able to call that procedure that's ultimately defined in an ASM file, in an assembly file. And that's another way to interface between the two as well, or combine your C++ with your assembly, is just have the assembly procedure in a different file and then call that procedure as many times as needed from within the main C++ program. And so we'll look at the syntax for that as well. And what you'll see in the example is that we can create a prototype for the assembly function in a header file. And then in the assembly file, what we need to make sure is that everything lines up with what we did in the C++ side of things. So we'll also see the basic idea of what a prototype looks like at the assembly level, but we'll see also how it's going to match up with what we did at the C++ level, meaning the parameter list, because whichever direction you're going in this case, we looked at an example of where we were writing out the function call in assembly, and we were calling a function written out in C++. And now we're essentially going to look at the other way around, right? Where the function call itself is going to be in C++ code, right? But the function that we're calling is written out in assembly. But either way, we just have to make sure that we match everything up. So we know that with C++ function call syntax, you have the name of the function, and then you have the parentheses with whatever arguments you're going to pass in. And that needs to line up ultimately with your assembly code. And so in the assembly function, we can define, if we want, we can do a prototype, and that's going to match up with the header part of the function. Similar to how in C++, right? If you write out a prototype, that prototype needs to match the way that you set up the header of a part of the function body. So we'll see that as well, and how that's going to work out at the assembly level. And so we'll see the basic idea of setting up a prototype at the assembly level. But there's a couple of key things that we'll see. So again, what you're going to see is there's going to be the C++ program itself, right? Meaning the CPP code. There's going to be a header file that has a prototype of the assembly function. And then there's going to be the assembly file where we can define a prototype and then the actual function itself. And so in that header file, which is still written out in C++ code, we're going to be defining a prototype for the function, but the function is not defined in C++, right? But rather in the assembly file. And so we have to form that connection between these different files. And so it's going to be very similar to a standard C++ function prototype, but there's going to be a couple of keywords there that are used in the prototype. And one is the keyword extern, which just signals the fact that the function that we're declaring the prototype for is declared or defined externally in a separate file. So we'll have the keyword extern there, and we'll also have the keyword C there as well. And really on the C++ side, that's the only thing that is maybe a little bit different than what you're used to, is that extern and the keyword C, right? The rest of the C++ code is just going to be standard C++ code, but we are going to have that extern and that keyword C as part of the prototype. And so together, that's going to allow it to know that that function that we're defining the prototype for is actually defined in another file, which happens to be an assembly file. And then we'll look at also what the prototype at the assembly side looks at as well. So this is the CPP file, and the idea with this, basically this is just a program that's supposed to search for a value and see if it occurs in the array. So we have an array here that's going to be storing some random numbers, and then the user is going to be able to type in a number, and they're going to be able to see if the number that they typed in occurs in the array or not. But the function that does the actual search logic is written in assembly rather than C++, but everything else is in C++. So the starting point here is the main function at the C++ level, which is also where we define the array, among other things. And then we do things like get some user input, and then we call down here in this loop this function called index of. And that function is defined in assembly rather than C++ directly. And so the way that we set this up was in this H file, which is called indexof.h, we have a C++ style prototype, right? Or what looks very similar to that. So the name of the function is index of, return type here is long in this case. And then we have these three parameters, where the first parameter, the one that we're calling n here, that's going to be the value that we're searching for. And then we also have the array itself. And what's going to happen is these three parameters are going to be matched up directly with the assembly function. So this prototype here has to match up with the way that we set up the function at the assembly level. So here, all we're defining is a prototype. We're not actually writing out the actual logic, because the logic of the function is going to be written out in assembly. So the function call again was down here. Was down here in this part of the C++ code. So in the call here, the first thing is the search value, the value that we want to search for. The second one is the name of the array. And then the third one is the size of the array, which correspond to the three parameters here. So search value, array name, and then also size of the array. And then we also have this extern C here, where in particular the extern is just saying that this is going to actually be implemented externally, meaning in another file, which is going to be the indexof.asm file. And if we go into that file, so the index-of.asm is where we have the actual implementation of this function. So it's going to be done in assembly rather than C++. And again, here we have the idea of what the prototype would look like for the function. Although we do the same thing in the actual function header itself. But here we have index of, and then the word proto, which is short for prototype. And then we have three things here, you'll notice: search val, array PTR, and count. And the idea is that those three parameters correspond to what we set up on the C++ side. So for example, search val here, and you'll notice we said search val and then dword, or 4-byte value, right? That corresponds to this parameter. And then the second parameter, which we gave it the name array PTR, and then the type here is pointer to dword, meaning it's storing the address of something that's a dword in size. That corresponds to the array parameter, because we know that when you pass in an array as a parameter, what you're really passing in is the starting memory address of that array. And then the last one here was just dword again, and we gave it the name count. And then that was going to match up with count here. So that's what we mean by the issue of correspondence, right? We have to make sure that that lines up with what we did on the C++ side, but we did just that. So the idea really is that the first parameter and the last parameter, those are both just dword values, right? 4-byte values. The second parameter is also, because it's a memory address, right? It's also a dword value, but we put the PTR there, right, because of the fact that it's an address really rather than a value like a number. So PTR, in this case, it really means pointer to dword as far as the value that array PTR is storing. So search val and count are both storing values, like numbers, whereas array PTR is storing an actual memory address, which in particular is the starting address of the array that's coming ultimately from main in the C++ code. And then the idea, similar to what you would do in C++, right? Because if you write out a prototype in C++, then your corresponding function header, right, has to match that. So in the actual function itself, which starts down here, so this part up here is just the prototype, and then down here in the code segment, we have the actual function itself. What you'll notice is that we really just repeated those three things again down here, because this is the function header part, right? So here what we said was index of proc, and then we have this uses here, which we'll talk about, and then we have the search val dword array PTR, PTR dword, count dword. So just the same three things that we had up here. And then as far as this uses, what that's going to do is it's going to push the values of those three registers at the beginning of the procedure, and then it's going to pop them at the end. So the uses operator is just a quick way to do some basic saving and restoring of registers that you know that you're going to change in the function body. So rather than pushing them one by one with separate push instructions and then popping them one by one with separate pop instructions, the uses operator is going to do all of that automatically for you. So when we say things like uses ECX, ESI, EDI, behind the scenes, right, it just means that it's going to push those three registers back to back at the beginning of the function, and then it's going to pop them back to back in reverse order at the end of the function. But our primary focus here is on these parameters and the fact that this, in the actual function header part of the function body, that this matches what we had in the prototype, and that all of it matches what we did on the C++ side. But that's exactly what we have here. So at both the C++ level with what we did here, and now at the assembly level with what we did here, we have a function that's ultimately defined to work off of three parameters, where again, the first one was the search value in terms of what you're searching for. The second one was the starting memory address of the array, which is a 32-bit address, but we also put the word PTR there to signify the fact that it's a pointer value rather than a, just a number value, and then count, which is the size of the array. So everything here is relative to size D word as far as the size of the 3 parameters. But for the second parameter, we also put PTR before D word, meaning pointer to a double word. And then the function itself is just doing a linear search. So just a basic linear search using things like what we've been talking about, right, with loops and, and jump instructions and all that. And you'll be doing something similar in your assignment, but it'll be a different function doing something different than compared to what we're doing here. But the idea is in the assignment, the overall setup of the 3 files is going to be very similar to what we're seeing here. It's just you'll be doing a different function. Instead of linear search, you'll be doing a function that deals with longest increasing sequence, as you'll see later today. So at this point, now we just have, right, just kind of, standard assembly code. But we're seeing in terms of syntax how to set this up. So the main thing is that we needed to make sure that we match up our procedure with what we did in the C++ code. Right, so again, but we have that direct correspondence. So search val, again, corresponds to n. Array PTR is going to correspond, for example, to what we called array here. Count corresponds to count. And just a little bit more there about the different parameters. So ultimately they're all D words in size, right? They're all 32-bit size parameters, but we know that the middle one here is actually storing an address, whereas the first and third are storing 32-bit numbers. So that's why it's also good to use that PTR keyword there for the middle parameter as well. And then again, we just needed to make sure that that we have this down here as well. So again, here, whereas this is just simply a prototype, this is the actual function itself. And so we can think of this part up here as the function header, right? Similar to how at the C++ level, right? We distinguish between the function prototype and the function itself. And in the function itself, that top line where we have the return type, name, parameters, we usually call that the function header. So just in the same way, what we're seeing here is ultimately that the function header, matches the function prototype. So we're just seeing that we're essentially seeing that same three things again down here that we had up for the prototype. And that's all we have to do again. So it's not really that much in terms of actually setting it up. We just have to make sure that ultimately that all of this, it lines up also with what we did on the C++ side, which it does, because everything in this case, at least, everything is relative to size D word. The only distinction being that the middle parameter is also furthermore an address, right? A pointer really. So that's why we put the PTR there. But they're all 32-bit size values. And then this is just the logic for the actual search algorithm itself. But that's the idea, is we have the linear search done in assembly, but everything else in the program is done in C++. So this is an alternative, right, to just doing the assembly block. And here this is convenient because now we have all of this logic in one place, right, one function, and we can call that function as many times as we want from the C++ program. So some cases, right, it might be convenient to break out at certain points with assembly blocks, but in some cases, certainly, it's going to be more convenient to actually just have an entire procedure that you can call instead of just always embedding it directly in the C++ code with the __ASM directive. So in this case, it was more convenient really, especially since we're calling the function multiple times, to just go ahead and implement it in a separate file as its own procedure, and then just simply call that procedure from the C++ level, which is exactly what we're doing here. And again, so that was our major focus here, was just kind of looking at the basic syntax and setup here. We did also see the uses operator, which again was just going to manually save and restore those registers. So it's going to save them at the beginning and then just restore them at the end. But that's the basic idea here in terms of syntax. And then here on the C++ side, and the C here is also something that we're using as well. The general idea, without getting in too much detail here, is that C++ will try to do what's called name decoration with things like overloading of functions, where it'll actually make the full name of the function include things like the return type and the parameter list. But that can cause problems when you're also working at the assembly level. So what that C is going to do is it's just going to tell it to not do that. Because the problem also is that different compilers might do might actually handle the name decoration in different ways. And so that can cause problems when we try to link that up with the assembly. So the C there just is saying to not, right, to not do the name deprivation. But again, the example of that whole idea of name decoration just means um, including things like return type, for example, um, or parameter types in the actual name of the function. But the problem is that in general, this could be handled different, potentially by different compilers. But an example could be something along the lines of, for example, int index of, something like that. But there's no real guarantee in terms of what it's going to actually do. But usually it's going to include things like the types of the parameters in the return type, but there's not really a universal way of handling that. So the C here is just turning that off, essentially disabling that. And then the extern is just saying that this is going to be defined externally in a separate file, which in this case happened to be an assembly file. So that's the connection between the two here. So, but the main thing was that we had to match this up, as we saw, with our things like our function header and function prototype at the assembly level, which we did. And then the actual function call was coming from main, right, in the C++ level. In particular, on this line here is where we're repeatedly calling that index of function. And so that's the basic idea. So most of the code here is in C++, but we do have that one function defined in assembly. And then when we run this, we can, for example, type in a number. And then it's just going to tell us, in this case, either found equals true or found equals false, depending upon whether that number that we typed in. So the numbers themselves are randomly generated. Let's do it again. Yeah, the extern seat. So those are that's not actually part of like the function name. Those are essentially extern is a keyword and then C is a specifier. So, and because those things could be applied to other functions as well. So in this case, we only had one external function, meaning one function that we were defining in assembly. Because in the entire program, right, there's only two functions. There's the main function from the C++ side, which was written out completely in C++ type code. And then there was the index of procedure, which was written in assembly. So the extern and the C they're not really part of that particular function, but they are things that we're applying to that function. So that's a distinction that we have to make there. So we could, if there were other functions, right, you could potentially apply them to those functions as well. Meaning, because you'll notice here that in this case, we wrapped it within curly brackets, but the idea is that you could also potentially have other functions besides index of declared within these curly brackets, and then extern C would be applied to all those functions, meaning we would be saying that all those functions would be externally defined, and then further that we're also disabling the, in this case, the name declaration with the keyword C there. So that's just the letter C in the quotes there. But so the prototype itself really is just this much. So just kind of a usual C++ style prototype with return type, name of the function, and parameter list. The extern C is not really part of the prototype directly in the same way that these things here are, but it is being applied to it, right? Meaning we're applying both extern and C. Oh, so the function name will have to be the same as the well, the function name here, yeah. The function name here has to match this, because what this is really just saying is that it's in a separate, yes, that it's looking for it in a separate file. So rather than defining that directly here, as you might do in just a straight C++ program, right? Because you might have the prototypes even in the same file as the actual function definition. Here we're just saying that whatever we define here is going to be in an external place. Because again, it is possible that we could have even more than one function within the extern C. The name of the file, I mean, we did call it index of ASM in this case, just because just kind of be consistent between these. Really could be any file name, but the name of the function is going to be the same, right? So index of in both places, meaning here, and then also here in the assembly file. So that's the idea with the other approach here. So in this case, we didn't use the ASM directive, but because we instead used a separate function or procedure, and again, that was more convenient here because, especially since we want to do the procedure several times, just, it's a lot more convenient to actually have that as its own procedure rather than just, embedding it within an ASM block and then trying to repeat it that way. So here we didn't have the ASM block, but instead we just repeatedly called that function, that procedure over and over from within the for loop itself. Okay.